and he will tell us about unexpected isomorphisms in hyperkähler fourfolds.
Yeah.
So all that I've done during the first half hour is here, and of course that's about half of what I wanted to do, as usual. So, but still I'll continue. So I sort of presented the bits and pieces of a theory of K3 surfaces, and so I want to explain what happens in higher dimensions. So in higher dimensions, the analogs that I want to talk about are called either hyperkählers, I mean for reasons that I want to explain, hyperkählers manifold, or irreducible, holomorphic, symplectic, varieties. I mean, everything is smooth. I don't know why I use varieties or manifolds. Okay, and so the abbreviation I'll use is HK because it's just shorter than IHS. Okay, so what is the definition? So, well, let me erase instead of just changing a few words. Okay, so for me, hyperkähler manifold is, so it's a manifold X, which is Kähler, and so we assume sort of similar properties that we had for K3 surfaces. So I would have, I could also call them S, I guess. But okay. So we assume that the space of holomorphic two forms is generated not by a form that vanishes nowhere, but by a form which is everywhere non-degenerate, which is the same in dimension 2, but. Okay, so in particular, the dimension of X must be an even number. Okay, and I'll still assume that H1 OX is 0, so that's mainly to avoid sort of abelian varieties. And so I guess the reason why K3 surfaces are interesting are the same. So this is when m is equal to 1, this is nothing new. It's a K3 surface, right? So now, much less is known about these varieties. And actually, I mean, on the one hand, there are not many examples, but still much less is known. Okay. And so let me mention a few general facts before I sort of specialize to more concrete example. So the first general fact is that there is, so you see the in the case of K3 surfaces, we made use of this the intersection form of the H on the H2. Okay, so here a priori there is no reason why H2 of xz should have any kind of naturally defined quadratic form, but there is one. So it's called, it has many names, but let me call it the Beauville form, okay? I guess Fujiki should be here also. So I won't give you the definition. I think I found a definition which I didn't know, which is sort of quick to write. So first of all, I should say that it's an integral form. I mean, it takes integral values. Okay, And so there's one definition which I found in, I don't remember where, which is as follows. So it's not really the Beauville form, but it's a multiple of it. So it's the integral over x of the square root of dot x. This makes sense, I guess. Okay. But we're not going to use this. The thing that we're going to use, so there's some number here that I don't know, and you don't want to know. So Q, the Beauville form Q is some rational multiple of this. And so the form that we'll use will have the property that whenever you have a class in H2, x to the 2m, so that's going to be an element in H4m of x, which is z, so that's an integer. That's going to be some number, which is called the Fujiki constant, times a q of x to the power m. That's the same m here, half of the dimension of x. Okay. So it's sort of surprising that the 2m intersection, self-intersection of a form on H2, which is homogeneous of degree 2m, should be the mth power of a quadratic form. But that's the case. Okay. So that's one thing that I'm going to use. The other thing is the fact that there's a modernized space, which is still stated over there for K3 surfaces. So again, so we can use the same tools. So quickly, what we needed is that there's so I want to talk about modernized spaces for polarized HK manifolds. And so the first thing that we need to know is that there's if you take an ample line bundle, there's a uniform power of it, which is very ample. So then you can use it to embed your manifold into a fixed projective space. Okay? So that's provided by Matsuzaka big theorem. It is called big theorem, right? So which says exactly that. There exists a number, so not mk, k naught, which depends only on, let's say, q of L. I think there's a little subtle thing here, maybe not. Well, it depends on L to m. Sort of the degree of the ample line bundle. So here, HL is a polarized hyperkähler manifold. So there exists an integer like this, such that for no, this is badly stated here. Let me call that D. Such that for all XL, hyperkähler and L ample with L hyperkähler of dimension 2m, such that you have this, LK is very ample. For all k greater than k naught. Okay? So this number for K3 surfaces was just 3. Okay? So in Matsuzaka's big theorem, this number was not explicit, but it's been made explicit by Donagi and Hsu and maybe other people later on. But very large, sort of a double exponential. But it's also a very much more general theorem, which does not only apply to our case. Okay. So using this and Vivek's theory, again, we can construct.
So M here can be of any dimension.
No, fixed dimension. Yeah, well, the M is here, yeah. You need the M in the statement anyway. Okay, so there is a same thing, okay, quasi-projective coarse moduli space. I won't give it a name for hyperkähler 2M folds polarized of given degree. Okay, so far I haven't given any examples, so maybe it's time. I mean, these spaces could be empty after all, and then there wouldn't be much point in this talk, but there are examples which were constructed in any dimension by Beauville. So let me just explain one series of example, which start from a K3 surface. So S is a K3 surface, and so we look at the what people call the Hilbert scheme of a subscheme of S of length 2. So Hilbert 2 of S. So the set, as I said, the set of subschemes of S of length 2. So you have two kinds, either two distinct points or a point with a tangent direction. And so a shorter notation is just S square like this, because it's almost like the square of S. And so the actual construction in that case is pretty easy. And so it goes like this. You take S cross S, you blow up the diagonal. Okay. And then you take the quotient by the involution that exchanges the two factors. Okay. And that's, you can take that as a definition. And so this is a hyperkähler fourfold. So in that case, the H2 is can be computed, and one finds that it is the direct sum of H2 of S Z plus a class which is usually called delta, where 2 delta is the class of the exceptional divisor on this. So the exceptional divisor, of course, corresponds to of the blow-up corresponds to these guys here. Okay, and so the only manifolds that I want to consider today are deformations of these guys here. So it turns out that these manifolds, these fourfolds, can be deformed into smooth hyperkähler fourfolds, which are not of this type. Okay, so I'll explain more about it. But so usually they are called hyperkähler fourfolds of K3 square type. Okay, what else should I say? Well, in that case, the Fujiki constant is equal to 3. Okay, and Okay, and there is actually a more precise description of these moduli spaces. So remember, for K3 surfaces, we had an irreducible moduli space for each degree. So here the situation is a little bit more complicated. So for each degree, so degree here could mean different things, but for me the degree will be the value of this Beauville form on L. Okay, so this is not, remember, L to the fourth is equal to 3 times Q of L squared. So that's another integer that you could call the degree, I guess. For each degree, positive degree, there is a irreducible moduli space of dimension 20 for hyperkähler fourfolds of type of K3 squared type. Okay, so okay, for polarized, so I want to say of degree 2n, but actually that's stated like this. That would not be true. You need to, there's another integer which sort of distinguishes polarization of the same degree, which did not occur in the K3 case. That's the divisibility. So the divisibility of an element of a lattice. So here we have this lattice. So remember, so maybe I forgot to say that. As a lattice, this is the K3 lattice. And the Beauville form on this guy here takes value -2. So this lattice is not unimodular anymore. And so you have the notion of divisibility of an element of the lattice. So the ample class here will be an element in here, so an element of the lattice. And the divisibility of an element, let's say x or alpha of a lattice gamma, is the positive integer gamma, such that if you take the intersection of alpha with all elements of the lattice, they're all multiple of gamma. Okay? So this is called the divisibility. So of course, in a unimodular lattice, the divisibility is always 1. Yeah, polarization is always primitive. Yeah. I mentioned that during the first talk. Okay, so anyway, in that case, you have an irreducible moduli space, which quasi-projective, which I denote by this letters here. Okay, so I wanted to, as I did for K3 surfaces, I wanted to try to describe, so what is the geometry of polarized hyperkähler fourfolds of this type of low degrees. Okay, so remember, for K3 surfaces, we had a pretty complete description. It turns out that for hyperkähler fourfolds, there's not much is known. Okay, so let me begin with the n equals 1. Okay, so the n is not the dimension; it's so 2 is the degree of the polarization. So maybe I should mention the fact that there is a Riemann-Roch theorem also on hyperkählers, analogous to the one I use on K3s. And for us, it takes the form that H naught of XL is equal to the Euler characteristic, and by Riemann-Roch, this is like this. Okay, so remember Q of L is 2n. So this is going to be 1/2 of n plus 2, n plus 3. L is ample, yeah. You're right. Well, let's say polarized. Okay, so when n is equal to 1, you get a rational map from X to P5. Okay, a priori it's a rational map. And in that case, and you may wonder which map do you exactly do you get? Okay, remember in the K3 case, we were able to identify every time, for low degrees, the image, and we said that we had a complete description. So here, in that case, let's say for most of the time, so for XL general, so you could also see that the usual degree, L to the 4, is equal to 3 times 2 squared. That's 12. Okay, so phi L could be birational onto degree 12 hypersurface, which is probably what you would expect, but that's not the case. So it was proved by O'Grady that phi L is 2 to 1. It's a morphism. It's a 2 to 1 onto a sextic surface, not surface, a sextic fourfold. So in particular, L is not very ample. Okay, so yeah, so the next case already the situation is not well known. So there is no geometric description of a general XL. There are, however, some particular cases which can give you an idea. And so this case is the following. So take S in P4, a K3 surface, as explained in the first part of the talk. So it's a complete intersection of a quadric and a cubic. Okay, and so I consider the map. So let's say it's general. And I consider the map from the symmetric, the Hilbert square of S to the Grassmannian of lines in P4, which sends 2 points here to the line that it spans, that they span. Okay. And then I embed this by the Prucker embedding in P9. Okay. And so what is the corresponding linear system? Well, if you so you pull back the O of 1 here, and the corresponding L is F. That's the polarization on S minus delta. Okay, so the delta is that class here, and the L corresponds to this factor. Okay, and if you compute the Q of L, so this is going to be 4. It's 6 minus 2. So this gives you an example of a polarization of degree 4. Okay, and so you can see, if you look at it a little bit closely, this map is not, so it's certainly a morphism. So let's say that S contains no lines. This is certainly a morphism, and it is birational onto its image, but it's not an embedding, because, so you have a quadric here, so it contains lines, okay, a P3 of lines, And so these lines will intersect the cubic into 3 points. Okay? Now, if you take any pairs of 2 out of these 3 points, they'll go to the same line. Okay? So this is not injective. It is actually the normalization of the image, but the image is singular. Okay? So all you can say is that in that situation, phi L is birational. Which will certainly be the case for a general X. So the question you can ask, I think it's not known already, is phi L, is L very ample when X is general? Okay. So by the way, I didn't specify the divisibility here. You can show that divisibility 2 can only occur when n is congruent to -1 mod 4. Okay, so divisibility is 1 in these 2 cases. Okay, so the next case is n equals 3. So we have 2 possible divisibilities. It turns out that in the case when n is equal to 3 and the divisibility is 2, as in the case where n was equal to 1, there is a geometric description of a general XL. Okay, which is lacking in the case of when n is equal to 2. Okay, and so this is the old work by Beauville and Donagi. And they describe a general XL with this type of polarization as follows. You take a cubic hypersurface in P5, smooth. You take the space of lines contained in W, so usually called the Fano variety of lines, even if it's not a Fano variety. And so this, of course, sits into the Grassmannian of lines in P5. Okay, and again, by the Pluk embedding, this goes into P14. So Beauville and Donagi proved that this is a general hyperkähler fourfold with this characteristic. And so this is the map here that I'm describing, which is obviously an embedding, is the map associated with the polarization. Okay. So in particular, L is very ample. L is very ample on the general XL. And so the way they prove that it is a hyperkähler fourfold, I mean, it's not obvious, is they actually find a special kind of cubics, which are called Pfaffian cubics, for which they prove directly by a very nice geometric construction that this is equal to the Hilbert square of S. Okay. So S is a K3 surface of degree 14, which I did not describe in the first part of the talk, but there's a Mukai description of these surfaces. Okay, so you can ask about the case where gamma is equal to 1, and actually I don't think there is a general description known of this case here, but you can do the same trick as I was doing here. I mean, obviously, this construction can be made for K3 surfaces of any degree. Okay, and so you find in that case that for that example, that L is also very ample. So that extends to the general member. So, so this is sort of an unexpected isomorphism between hyperkähler fourfolds. Okay, so hence the title of the talk. Now that it's almost the end. No, but I started a bit after 2:30, no? Okay. So let's see. There are other. I don't have time to explain that, but there are descriptions of general hyperkähler fourfold with polarization of given degree and divisibility. Only in two other cases. Okay, so I mean, a general question would be find more. I mean, problem more than a question. Find more geometric descriptions of general hyperkähler fourfold. With a given type of polarization. So in other words, n delta, n gamma. Okay. Small for small n. So it's more a problem than a question. Actually, there's another question that I would like to ask, which I never thought about. So maybe the answer is known, or so another question would be to remember for K3 surfaces, there's this theorem that says that whenever you have an ample line bundle, its second tensor power is base point free, and the third tensor power is very ample. Do you have here a similar statement? So we know that there is an integer which only depends on the numerical data, for which L to the k is very ample. That's Matsuzaka's big theorem. But I mean, so is L squared? I don't know. I mean, this is probably trivially false, but maybe not trivially. But if it is, then you just change the number here. So if L squared base point free, always. I mean, always. Let's say for our fourfolds, and is L cube always very ample. Seems to be difficult. I mean, you want to have something which is true for all hyperkähler fourfolds. So I don't know. So another very important result is the fact that the Torelli theorem holds for polarized HK fourfolds. I mean HK of well, actually for all hyperkähler. Okay, so this is a result of a recent result of Verbitsky. And more or less all the results that I mentioned about K3 surfaces are much older. So Torelli theorem in either forms that I explained earlier, either sort of whenever you have a Hodge isometry between the H2s of two hyperkähler fourfolds, then it is induced by an isomorphism between the polarized fourfolds. Or you can also state it in terms of the period map. Okay. Are there any questions? Yes.
So in this case, can you describe the image that is a single?
Here?
Yeah.
Not really. I mean, so it's a fourfold into a sixfold here. So, but it's singular. So, yeah, it has sort of this triple locus here, which comes from identifying these three pairs of points here. So I don't know. I mean, I haven't looked at it very closely, but yeah. There is another, so this sort of varieties of this type represent a hypersurface in the moduli space. So you have a whole hypersurface where there's this behavior here. There's another hypersurface that has been described by Iliev, Kaputskas, and Ranestad, which says that they have another hypersurface for which the morphism associated with L is 2 to 1 on 2 or something. Okay. Yeah, but I think that's that should be doable to find a geometric description. Okay, so what do I want to do now? I'm not completely sure, actually. This is why I'm. So I mean, it's more. I'm more like telling you a story than. There's no. I don't have any big theorems, but I think it's a nice story. I mean, you may wonder whether I have any theorems at all, actually, but. So the game that I want to play is sort of use Torelli theorem to prove this unexpected isomorphisms. Okay, so let me maybe explain what I mean by that. Okay, so let's say you want to find inside a given moduli space. Okay, so it's over there. So in other words, you fix the degree of the polarization and the divisibility. Fourfolds are isomorphic to Hilbert square. So the first condition, if you want X to be isomorphic to S square, is that, so now it's gone, but you need the Picard number to be at least 2. Okay? Because I didn't really mention that, but the Picard number in S2 is always at least 2. There's a sort of a line bundles that come from S, and there's the exceptional divisor. Okay? And they are linearly independent. Okay? So that's sort of a necessary condition. And the fact is that for a very general element, in here, the Picard number is 1. Okay? So you need to be inside what is usually called the Northeastern locus. Okay. So this question was originally studied by Brandon Hassett, who is here on the first row, second row, in his thesis, so some time ago. In the case where, so Hassett, when n is equal to 3 and gamma is equal to 2. Okay? But that was before the Torelli theorem, so he had to work much harder than we have to now. So his conclusion was that there are actually infinitely many hypersurfaces in the moduli space which correspond to guys which are really isomorphic to Hilbert squared. And so the first thing that Brandon had to do was sort of to describe this Noether-Lefschetz locus. And so the way he did this was was as follows. So let's say you want to look at points where the Picard rank is 2. So it means that you have a rank 2 lattice in H2. Okay, so you have a rank 2 lattice inside, let's say, H2 of X. Which contains the polarization. Because I'm only looking at polarized stuff. So then there's one obvious invariant of this lattice, that's its discriminant. So let me be a bit imprecise here. It's more like the discriminant of the orthogonal, but let me forget about this detail here. So one way to sort of parameterize the Noether-Lefschetz locus, so let's say it's going to be the union over, let's say, all integers d, actually positive integers, such that, let's say, x, or pick x, contains a rank 2 lattice of discriminant d. Let me forget about that. So the nice thing about Torelli's theorem is that this is a property that you can translate in the period domain. Okay? Because this is something that you can read on the period. So in this way, so remember we had this, I mean, I never defined it, but so we had the period domain, so period map, which I never, so which goes from M gamma to N to some quotient by some orthogonal group of, here we had a period domain. In this period domain, each family like this represents sort of a hyperplane in here, okay, which is more or less the orthogonal of this sublattice of the fixed lattice here. So we have here infinitely many, countably many hypersurfaces. So the period map is an open embedding. And so this component of the Noether-Lefschetz locus actually would be the inverse images of these hypersurfaces in the modernized space. Okay? So the thing is that you can actually, in a lot of good cases, these hypersurfaces are irreducible when they are not empty. So this is the study that Brandon did in that case here, which you can do in general. And so now if they are irreducible, it's sort of if you're lucky, it can be easy to describe their general elements. Okay. So in other words, now I want to make a link between this discussion here and that problem. Okay, so let's go back to this thing here. So I said that the Picard number was at least 2. Not only that, but the Picard group of S2 always contains, so there's an element which comes from the polarization on S, and there is this extra class that's only on the Hilbert square. Okay, so if S has degree 2e, same notation as before, the matrix of this guy here is like this. Okay, this is an orthogonal sum. Okay. So you find that your X here must be special for a rank 2 lattice with a discriminant minus 4e. Okay. Actually, you want to change the sign, but it doesn't matter. Okay. If you count parameters, so remember that a polarized K3 depends on 19 parameters. Okay. And so if you vary S here, you'll get something which is 19-dimensional. So I said here that the components of the Noether-Lefschetz locus are 19-dimensional. Okay. So in other words, if you manage to put this into that setting here, you'll have a description of a general element of one component of this guy here. So what do you need to do for that? Well, first of all, there's something which is missing here, is that there is no polarization, no given polarization on S square. I mean, you know there's one because it's a projective variety, but it's not apparent here. The F here is not ample on S square. Okay? So you need a polarization. And this polarization, if you want this construction to work in general, you want it to be a linear combination of F and delta. So let me write it as BF minus A delta. Okay, and then it will have degree. So F square is 2e B square minus 2 A square. Sorry, that's 2. So if you want to have a polarization of degree to n, you first need this equation to be satisfied. Okay. So this is a Pell-type equation. Okay. Although it seems that Mr. Pell actually never worked on them. It just translated an article by someone else, but still, his name stayed. And so that's the first condition. There's the condition about the divisibility. So F belongs to a unimodular lattice, and so the divisibility is either 1 or 2, and it's easy to check that gamma will be equal to 2 if B is even, and to 1 if B is odd. Okay, that's very easy to check. The other thing that you want to know is that L is ample. Okay, that's a non-trivial question, and it requires to know what is the ample cone in the case where a peak of S square is equal to that. Okay? And fortunately, this is known by work of Bayer and Macrì. I don't know. I think it's like this. Huh? I don't understand accents in Italian. But anyway, so they describe the ample cone, and the ample cone is actually I mean, it's a two-dimensional cone, so there's not a lot of choices. So here you have the two generators, F and delta. Delta here, no. I mean, there's no reason. And so F is a spans, F is nef and big, so it spans a, it's nef but non-ample, so it spans a one of the rays. And the other has a certain slope. So that's the ample cone here, the interior of that cone. And they compute this number. It depends only on the degree of the polarization. Okay, so nu E is known. Its value is also, I mean, it's sort of solves a conjecture of Hassett and Chinkel, and it's also computed. It's always a rational number, by the way, and it's computed using equations of this type. So for L to be ample, you want its class to be in that ample cone. So you want A over B to be smaller than nu E. And as I said, there's no, I'm not giving you the value of nu E because there's no formula. But if you give me an integer E, you can compute everything. So what's the upshot of all this discussion? Conclusion of this. So how can we phrase this? Well, so let's say you have various integers, A, B positive, E positive, and I take S, a K3 surface with a polarized K3 surface with a polarization of degree 2E, and I consider the class BF minus A delta. If I make this assumption here, then I know that this class will be ample on the Hilbert square of S. Okay. And it will give you an element of one component of the Noether-Lefschetz locus for hyperkähler fourfolds with polarization of degree n, which is given over there. Okay, so let me summarize that. So assume that you have this equation, I mean this inequality. That's the slope of the ample cone. And so you can define, say you can define the number n by this equality. Then what this construction tells you is that you can take a polarized K3 with a polarization of degree E, and you can send it to its Hilbert square with polarization BF minus A delta. Okay, this will give you a map from what? From the moduli space of K3 surfaces of degree 2E, which I introduced during the first part of the talk, K2E. And so this is valid only for sort of general S, so let me put a rational map here. And where do we land? Where we land in the moduli space of hyperkähler fourfolds of degree 2n and divisibility gamma, which is given according to the parity of B. This is certainly not going to be surjective because the dimensions is one less here. But what you do, where you do land is some component of this Noether-Lefschetz locus. So it has, so we call the indices here. And what I want to indicate here is the discriminant. Okay, so the discriminant was, I mean, it depends on your notation, but here, let's say a 2e. Okay. So this sort of labels the various components of the Noether-Lefschetz locus inside this modernized space. Okay. So this map here is a one-to-one map. It's one-to-one onto a component of this locus, okay? But if you are in a nice case, and there are cases where they are often irreducible, maybe often is too much, but there are cases where they are known to be irreducible, like in the case where that Brendan studied in his thesis. Well, you can, here you have a sort of a description of a general element in that locus. Okay? So if all these conditions are satisfied, then you get a geometric description of many elements, special in the sense that they are in the Noether-Lefschetz locus. Many special hyperkähler fourfolds. Of a given degree. And divisibility. Yes.
But I thought there were examples where that map was 2-to-1 on its image.
Yeah. Actually, not the way that I've set up the things. Yeah. I read your thesis, as you know, and yeah, but it's. Okay. So maybe a consequence of this is that for any given n and gamma, so remember that gamma can only take the values 1 and 2, and value 2 only when n is congruent to -1 mod 4. There are always infinitely many such hypersurfaces. Okay, so whenever you take a component of modernized space of hyperkähler fourfolds, you always have countably many. Of course, the infinite here is countable. Infinitely many hypersurfaces which correspond to Hilbert square of K3 surfaces, and their union is dense in the usual topology, of course. So the fact that the union is dense is actually sort of a general fact. Whenever you have infinitely many divisors in a Shimura variety like this, the union is always dense. It's a big theorem of Ulmo and Closet and Ulmo, I guess. Well, I guess I have to stop here. I'm not sure that the conclusion of all this is very clear, but so the idea is that you get sort of for a dense set of points in the modernized space, you do have a sort of a geometric description. Of course, that doesn't help you to find a description for a general element, but it can help you solve the sort of questions of whether L is very ample, or if you find one, for example, for which L is very ample, then you know that it's very ample in general. And so this, I wanted also to talk about, but I don't have any time left, but you can use this Torelli theorem also to analyze the automorphism group of hyperkähler fourfolds. Okay, so you find that they may have, interesting automorphisms and or birational automorphisms. So that sort of generalizes another article of Brandon and Chinkel, who studied that in a particular situation against before Torelli. So they had a very nice examples where you have a automorphism group which is a sort of an infinite diagonal group. So you can let's say Z2 free product with a Z2. Okay, so I'm going to stop here. Thank you.
Questions to the speaker? I have a question. Go ahead. You have infinitely many, but I gather there are infinitely many which are missing. There's a Lefschetz loci which are not on this side.
Yeah, I guess, yeah.
I don't know. I wouldn't bet my life on it, but probably, yeah.
That's a non-trivial
condition here.
Is there any chance of describing it?
Well, you can also, the thing is that there's not, how do I put it? You have to start from something you know. So here you know K2 surfaces, and so you can start, for example, for varieties of line in cubic, and which are also special, and then you map them. You choose another polarization, and you map them in another space here, so you get another description. But
do you have any examples of connections between other Lefschetz loci of higher dimensional hyperkählers?
I haven't looked at that. No. Yeah. So yeah, you can probably do that in higher dimensions also. Yeah. Yeah. Of course. Yeah. And the situation is a bit more complicated, modernized space, as you know, and stuff. But yeah, of course, yeah, there is no reason why you shouldn't be able to do that.